Welcome back, guys. So in the last video we classified semiconductors into intrinsic and extrinsic semiconductors, and extrinsic semiconductor was further divided into p-type and n-type. But on what basis did we classify the semiconductors? Now we classified the semiconductors on the basis of doping. With the Olympic Games going currently, if you come across this word, don't get surprised. Doping in the field of sports and athletics is the administration of drugs to enhance your performance. Okay, so it's illegal in Olympics and other sports. But in case of semiconductors, this is very much essential to enhance the conductivity of a given material. So the process of adding impurity is called doping. And what is an intrinsic semiconductor? A pure semiconductor free from every impurity is known as intrinsic semiconductor. Example: silicon, germanium. So we saw how they conduct electric current in the last video, and their conductivity depends solely on the number of free electrons excited from the valence band to the conduction band. Fine. And what is extrinsic semiconductor? The semiconductor in which the conductivity is caused due to the charge carriers made available from the external sources by adding impurity from outside are called extrinsic semiconductor. So in case of extrinsic semiconductor, impurities are added to enhance the conductivity by the process of doping. And to increase the conductivity of intrinsic semiconductors, two types of impurities can be added. One is pentavalent impurities. So elements whose each atom has 5 valence electrons, for example arsenic, antimony, phosphorus, and they are known as donor impurities because they donate extra free electrons to the semiconductor. And the other type is trivalent impurities. The elements whose each atom has 3 valence electrons, example aluminium, boron, gallium, and they are also known as accepted impurities since they accept electrons from the covalent bonds of the semiconductor. If we see those elements in the periodic table, you can see that trivalent impurities belong to the group 13 of the periodic table. So group 13 elements are used as trivalent impurities to enhance the electrical conductivity of a semiconductor, and group 15 elements are used as pentavalent impurity to enhance the electrical conductivity of the semiconductors. Now let us have a look at n-type semiconductors. When a pentavalent impurity is doped in a pure semiconductor crystal, then the conductivity of crystal increases due to surplus electrons, and such a crystal is said to be n-type semiconductor. So consider a silicon atom with atomic number 14. Its electronic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p2. So we have 4 valence electrons. And consider a pentavalent impurity, for example phosphorus with atomic number 15, and its electronic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p3, and we have 5 electrons in the valence shell. Let us consider a pure semiconductor material consisting of only silicon atoms. Let's say the central silicon atom is replaced by pentavalent impurity phosphorus. Now these adjacent silicon atoms will share their electrons to gain stability, and this phosphorus atom at the center has 5 electrons, which it will share with the adjacent silicon atoms. So this phosphorus atom, after sharing 4 of its 5 valence electron, becomes stable, and 1 electron will remain extra, and this acts as free electron, and this free electron helps in enhancing the conductivity of n-type semiconductors. And now let us have a look at p-type semiconductors. When a trivalent impurity is doped in a pure semiconductor crystal, then the conductivity of crystal increases due to deficiency of electrons, and such a crystal is said to be n-type semiconductor. Now you can write here due to deficiency of electrons or due to excess of holes. And we have just seen that silicon has 4 electrons in the outermost shell. And let us consider a trivalent impurity, aluminium. The atomic number 13 and its electronic configuration can be written as 1s2, 2s2, 2p6, 3s2 and 3p1. So it has 3 electrons in the valence shell. So again, consider a pure semiconductor material made up of silicon atoms. And now suppose this pure semiconductor material is doped with a trivalent impurity, and let's say this central silicon atom is replaced by a trivalent impurity, aluminium. These adjacent silicon atoms will share their electrons to gain stability, and we have seen that aluminium has 3 valence electrons, which it will share with this silicon atom, this silicon atom, this silicon atom, and in one of the bonds a vacancy will be created, that is a hole. In case of p-type semiconductors, holes help in enhancing the electrical conductivity of a semiconductor. Now let us have a look at some points of differences between intrinsic and extrinsic semiconductors. Intrinsic semiconductor, it's a pure type of semiconductor, whereas extrinsic semiconductor is an impure type of semiconductor due to doping. In an intrinsic semiconductor, density of electrons is equal to the density of holes. We have already seen this. Whereas in case of extrinsic semiconductor, density of electrons is not equal to the density of holes. An intrinsic semiconductor, electrical conductivity is low, and in case of extrinsic semiconductor, electrical conductivity is high due to doping. Intrinsic semiconductor, dependence on temperature only. Dependence on temperature as well as on the amount of impurity. The more the impurity, the more it will conduct electric current. The band gap between the conduction band and the valence band is small, and in extrinsic semiconductor, the energy gap is higher than the intrinsic semiconductor. Now let's see some differences between n-type and p-type semiconductors. N-type, it is formed when pentavalent atoms are added in an intrinsic semiconductor. P-type, it is formed when trivalent impurities are added in an intrinsic semiconductor. In n-type semiconductor, as we have already seen, the majority carriers are electrons because there will be excess free electrons, and the minority carriers are holes. Whereas in p-type semiconductor, the majority carriers are holes and the minority carriers are electrons. In n-type, the donor energy level is close to the conduction band and far away from the valence band. In p-type, the acceptor energy level is close to the valence band and far away from the conduction band. As you can see here in the diagram. In n-type, the donor level is close to the conduction band, and in p-type, the acceptor level is close to the valence band. But where does these levels come from? Well, that's where band theory comes in. Now if we apply band theory to n-type and p-type semiconductors, we'll see that extra levels have been added by the impurities to the semiconductor. In the n-type, there are electron energy levels near the top of the band gap, so that they can be easily excited to the conduction band. And in p-type, extra holes in the band gap allow excitation of valence band electrons, leaving mobile holes in the valence band. So that's it for today, guys. See you in the next lecture.